So hi everyone, I'm Nalini, and I'm a student with Polina Goland at MIT. And today I'm going to talk about machine learning across the MR imaging workflow. So this whole workflow starts when a patient comes in to be scanned. And when that happens, the data that's actually acquired from the scanner is the frequency space components of the image that we're ultimately interested in. And this is also often referred to case-based data. So there's actually an additional step that has to happen in going from this case-based data, which comes directly from the scanner, to an image which might be visualized by a researcher or a clinician. And then after that, there are a few more sort of optional steps in this workflow. So the image that's output after conversion from the case-based data might be post-processed or analyzed into some higher level representation. So this could be something like a segmentation. And then there can be even further analysis on that in order to generate metrics or values that provide some insight as to what's going on in the image. So we've already heard earlier today about examples of how machine learning can be used in the last couple of phases of this pipeline, both for scientific research and as a step towards informing clinical care. And in this talk, I'm going to focus a little bit earlier in the workflow on how we can use machine learning to actually do the conversion from case-based data to high-quality image-based data, even in the face of an unideal acquisition of the case-based data. And I'll get into examples in a minute of ways in which the case-based data that we collect might be corrupted. So in a perfect world, if we acquired perfect case-based data, it would be really simple to do the conversion to go from case-space to the image space. All we would need to do is apply an inverse Fourier transform, and then we'd output sort of a perfect image. The issue is that for a variety of reasons, the case space that we acquire might not be perfect. And so the idea here is to combine sort of the structure of the inverse Fourier transform, which we already know is useful from going from case space to the image space, with the additional power of machine learning, which we're going to use to compensate for sort of the issues or the reduction in information in the case space that's acquired. And for the next segment of the presentation, what I'm going to do is describe 3 settings in which we might acquire corrupted case-based data. And then I'll come back and talk through, for each of those cases, some previous work on how we can use machine learning to correct for that corrupted data. And then I'm going to end with an example from my own work of sort of a general purpose technique for how we can learn in corrupted settings. So the first example of the sort of difficult imaging scenario we might face is that of undersampled reconstruction. So as many of you might know, doing an MR acquisition is a pretty time-intensive process, and that long time period results in both a high cost of performing any individual scan and in a lot of discomfort for the patient who is being scanned. And so one strategy for mitigating those effects is to limit the number of measurements that you take while you're doing a single scan. So for example, when acquiring case-based data, you might choose to only acquire measurements at the lines that are highlighted in blue on this image. The issue is if you just do an inverse Fourier transform on that image, on that case-based data, you get an image that looks like the one on the right. And you can see that first, we've lost a lot of the signal intensity that would be present in sort of an ideal image. And also that there's pretty significant aliasing effects, which make it impossible to identify any of the really specific structures that we need to visualize. Another setting where we might have difficulty in doing this sort of reconstruction is in that of motion. And this is a particularly important one because the cases where you have motion, where the patient moves inside the scanner might be correlated with particular clinical conditions that we're actually interested in measuring and understanding. And so what happens here in terms of looking at the case space and the image space is that you start off with a particular image in a particular position, and that might look like the image that's in the upper left-hand panel of this set of 6 images. And that corresponds to one set of case-based data. And then partway through the scan, as you're acquiring measurements in the case space, the imaging subject moves, so maybe to look like the image that's in the middle upper panel. And it's difficult to notice these changes in case space, but this corresponds to a different set of case-based data. The image that's ultimately acquired corresponds to some combination or some mix of these 2 different case-based acquisitions. And if we zoom in on that acquired image, you can see there's a ton of these really odd distortion effects on the image, which makes it, again, pretty hard to identify individual structures that might be of interest. The last example of corruption that I'm going to talk about is a pretty generic one, and that's acquisition in the face of noise. So just like in any imaging technique, there's the potential for the acquired measurements to be noisy when doing MRR acquisition. And in this case, the noise is induced in the case-based data, but that also translates to lost image quality in the image space. So as I alluded to earlier, there's already been really quite a bit of work on using machine learning, and in particular deep learning, to deal with all of these effects. And almost all of that work applies processing that operates directly on the image space data after an inverse Fourier transform has been performed on corrupted case-based data. And so here are three kind of examples of that. The first one by Schlemper et al. From a few years ago deals with the undersampled reconstruction problem. And their idea is to use ideas from sort of standard image space deep learning techniques and combine those with a rule that insists that whatever image is output by the neural network is consistent with the data that's acquired in case-space. So the network that they propose is comprised of a series of alternating layers where you have one layer that's kind of a standard layer from a normal neural network, and that's followed by what they call a data consistency layer, which is just a check to make sure that the frequency space data corresponding to the image that you're reconstructing is the same as what was acquired from the scanner. And their network just alternates between these series of layers until it finally outputs an image, which is a higher quality version of the output image that you would get if you just did a raw inverse Fourier transform. Similarly, there's also been image-based processing approaches for the motion correction problem. So really just last year, Haskell et al. Proposed an approach that uses an image-based neural network as kind of a smart initialization for an optimization approach for this problem. So again, they start with some sort of corrupted frequency space data or case-based data, and they use an inverse Fourier transform to construct an initial guess of what the corresponding image might look like. And then what they do is they use a neural network to refine that guess of what the image might look like. That refined guess is fed into an optimization program, which estimates both parameters of when and by how much motion occurred throughout the scan, as well as an estimate of the underlying image. And that underlying image estimate is what's output as sort of the final corrected motion-free output. And they've sort of set up a system of equations which ensures that this output is consistent with the acquired data and some observed motion pattern. And the key here is that they use the neural network in order to decrease the time that it takes to perform this optimization problem. The third example that I'm going to go through of a previous work that uses image space processing to deal with one of these artifacts is by Manhone et al., again, just from the past year or so. And they use a really standard neural network architecture, but on individual image patches within a noisy image in order to correct for the noise problem that I alluded to earlier. Again, the kind of unifying theme across all of those examples, and there are many others that exist in the literature, is that most of the recent work in this area does all of the processing in the image space. And this is a good approach for one reason, which is that most of the deep learning based approaches for image analysis are designed to work on image space data, and we visualize these images in the image space. So we're pretty sure that the processing that's done by using these networks that operate on the image space are helping us get to images that are more visually understandable. On the other hand, there's kind of a missed opportunity here because all of the artifacts that I described are induced directly in the frequency space. And so we might think that it might be easier to correct some of these artifacts first in the frequency space before converting to the image space to kind of catch the problem where it arises. And so what I'm going to talk about for the last part of this presentation is recent work that I've been working on for the past 2 years or so on joint learning that occurs in both the frequency space and the image space to kind of get the best of both worlds. And I'm going to start by motivating how this is possible by looking at the correlation structures that exist both in image space data and in frequency space data. And to do this, I'm going to show you a visualization of this correlation structure in both of those two spaces. And the way that this visualization works is as follows. So in each image that I'll show you, there's going to be a circled pixel, and that's kind of a reference pixel that all the other pixels in the image will be compared to. Then each of the other pictures, each of the other pixels in the image are color-coded corresponding to their correlation with the circled reference pixel. And this correlation is computed across a large data set of images. So for example, in this image that I have up on the slide, the pixel that's highlighted as being red would have a highly positive correlation between all of the example values at that pixel across the data set and the pixel values at the reference pixel location. Similarly, if a pixel is colored white, that indicates almost no correlation between values at that pixel and the reference pixel. And if a pixel is colored blue, that indicates a strong negative correlation between that pixel and the reference pixel. So here are two examples of that visualization, and these are shown in the image space. So the top image shows this correlation visualization for MNIST, which is kind of a generically used machine learning data set. And the bottom shows this correlation structure specifically across ADNI, the Alzheimer's Disease Neuroimaging Initiative data set, which is maybe a bit more specific to the types of images that people in this community are interested in looking at. And you can tell that regardless of the data set, if you sort of zoom in on the region that surrounds the pixel of interest, there's kind of a hotspot of really high correlations. And so you can get a lot of information about what value you expect to exist at a particular pixel just by looking at the values of the neighboring pixels. And that's the characteristic that allows current image space approaches in convolutional neural networks to do really well. Because convolutional neural networks apply sort of these local convolutions, which only take in data about a small neighborhood and output some value corresponding to that local neighborhood. And these images that I'm showing on the slide suggest that those local correlations are enough to do a really good job of inferring what should exist at a particular pixel. Now on the right, I'm showing sort of the same calculations, but for the frequency space data corresponding to the same data sets. So the first thing you might notice is that there's this symmetry in these data sets, and that's actually not too important for what I'm going to talk about in the rest of this talk. That just relates to sort of natural symmetries induced by the Fourier transform in real images. But what is important to notice is that if you zoom in on the circled region, there are again these hotspots of high correlation that are really informative about the value that should exist at the center of these circled regions. And so the idea here is that just like we could use convolutions in order to do inference in the image space, we can actually just apply really similar techniques in the frequency space and do a good job of inferring data there. And this slide just shows exactly the same visualization, but across sort of a wider range of pixels and locations in both the frequency space data and the image space data. And you can see that the effects that I described in the previous two slides are pretty consistent across the image, and they're not specific to just one location or one point in the frequency space data. So with that in mind, what me and several collaborators have developed is sort of a fundamental neural network layer structure that allows us to do both frequency space and image space processing in order to deal with all of the types of corruptions that I mentioned earlier. So I'm not going to go into super fine details about how this layer works, but the key idea is as follows. The image on the bottom of the slide shows the structure of the layer, and each of the red blocks show parts of individual layers within the network that exist in the frequency space. And each of the blue blocks show parts of the neural network that exist in the image space. So an individual layer within the neural network is shown in the dotted purple box, and that layer can just be repeated several times to form the body of the neural network. And you can see that first, at each layer, there are both inputs and outputs that exist in the frequency space and the image space. And more specifically, zooming into the dotted purple box, when we start with the frequency space and image space inputs, we learn some sort of combination of these two. And we learn that combination, again, both in the frequency space and the image space, apply convolutions, both in the frequency space and the image space. And then based on that, the output of that convolution and with a domain-specific nonlinearity, we output a layer output that exists both in the frequency space and the image space. So I'm next going to show results of using this network directly to deal with the three imaging tasks and corruption techniques that I described earlier in the talk. So here are quantitative results for that across a large data set of these induced artifacts in a set of T1 weighted images. And what I'm showing here in each plot is the mean absolute error between the image reconstructed through our method and the ground truth image. So the leftmost column shows results for the undersampling task, the middle column shows results for the motion corruption task, and the rightmost column shows results for the noise corruption task. In each case, the dark purple bar shows the results from our architecture, which learns both joint frequency and image space representations. The red bar shows a purely frequency space neural network, and the blue bar shows a purely image space neural network. In each of these cases, because we're plotting error, the lower the value of the bar, the better the result. And you can see that across the data sets, across each of these tasks, and across different levels of corruption, which are each of the 3 values within each plot, the joint approach does as well as or better than the other 2 approaches. That's true across the data set, but we can go further and look at the performance of these methods across individual subjects within the data set. So the y-axis on this plot is the same. It's just the mean absolute error between the reconstructed image and the ground truth image. But on the x-axis, I just have indices corresponding to individual subjects that we tested this data on. And you can see that not only does the trend of our network performing better hold across large data sets, but this is true for almost every individual subject that we tested this data on. And to give you a qualitative flavor of what these results mean, I'm going to just zoom in on one of those points kind of in the middle of that left undersampling plot. And here are qualitative results for that. So what I'm showing here in the top row is the image space, either reconstruction or ground truth data. In the second row, I've zoomed in on an illustrative patch, which shows which networks are able to reconstruct what. The third row shows the difference between the patch that I've zoomed in on and the ground truth for that patch. And the final row shows the frequency spectrum of the reconstructed image. The key thing here is that if you zoom in on the image patch, so the leftmost column shows the ground truth data, which we started with and which we want to try to reconstruct. And the second column shows the input data. So again, this is an example from the undersampling case. And you can see that we're feeding the algorithm extremely corrupted data that looks like it's lost a lot of the content that we need to reconstruct. The last 3 columns show results of the individual image reconstructions from the 3 techniques, with the middle column being the result of our proposed joint technique. And you can see that there are really specific structures that our technique is able to reconstruct, that purely frequency space reconstructions or purely image space reconstructions, which are the last 2 columns, are not able to resolve. So the key takeaways from all of this are that first, just in general, machine learning is able to allow us to do image reconstruction that's robust to a variety of non-idealities in acquisition. And second, the takeaway that's kind of the salient point from my work is that if we try to use machine learning in a joint sense, so if we apply it both in the frequency space and the image space, this yields superior results for image reconstruction when we compare to just image space learning or just frequency space learning.